Yeah. Good afternoon, everyone. It's my great pleasure to be here. Since the first author, Huang Fu, he can't attend because...
Yeah, I would agree with that. I see them all sticking out. Yeah?
Is it the fact that the lights are in the room above us?
So because Huang Fu cannot attend because of visa problems, so I will present our work to the challenge. So depth estimation is a very fundamental problem in 3D vision, and it has many applications in like robotics and self-driving cars. So in this challenge, we are concerned with the problem of single image depth estimation, where we have no stereo correspondences or motion information. So doing single image depth estimation is much cheaper, but it's also much more difficult, because this is fundamentally a yield-post problem. Consider this simple example. The two planes in the 3D space will project to a same image in the camera. So given this one 2D image, there could be an infinite solution to this problem. So previous works, a lot of previous works on depth estimation have been proposed, and we can roughly categorize them to two groups. The first group is the shallow methods, and the second group is the deep methods. So the shallow methods usually extract the handcraft features from local patches and then apply like a Markov random fields to enforce global consistency. And for the deep methods, they have outperformed the shallow methods by a large margin in recent years because of their ability to learn the hierarchical features from a large number of images. Here's a typical pipeline for the deep learning methods. So given an input, we first feed it to a convolutional neural network, and then we get the prediction map. After obtaining a prediction map, we compare with the ground truth with a specific loss function, and we can propagate the error to update the network parameters. So there are two fundamental elements in this pipeline. The first one is the loss function. So most of the previous works focus on the regression loss because the depth value is inherently a continuous variable. And in our work, we consider this as a discrete variable, and we apply ordinal regression loss. And this improves the results by a large margin. Another thing is that the previous works on neural networks, they rely on progressively refinement of the coarse prediction to final predictions. On the other hand, we just train a neural network to output high-resolution depth maps by aggregating multi-scale features. So I will explain these two parts one by one. Consider loss functions. Probably the most widely used loss function is the mean square error. So we just calculate the square error on all the examples. As pointed out in previous works, the noise, distribution of the difference between depths is inherently a heavy tail distribution. As we all know, MSE is not robust to outliers. So many works have focused on designing more robust losses. For example, we can do MSE in the log space, or we can rely on a more robust loss function, such as mean absolute error. So all these losses are designed for regression. So how about discretize depth value to discrete values and then apply the classification network? This is our first attempt. And because classification completely ignores the ordering between the depth values, so finally we decided to employ ordinal regression loss for this problem. So firstly, we should have some method to discretize the depth range to a series intervals so that we can convert the continuous depth values to discrete values. A straightforward method would be to do uniform discretization in a depth range. In practice, we found that the estimation uncertainty usually goes up when the depth value increases. So to account for this issue, we propose to do a space increasing discretization method, which did uniform discretization in the log space. So in this way, we can capture, we can allow larger quantization area when for the larger depth values. To implement the ordinal regression loss, we take a very simple method. So we transform the ordinal regression loss into a series of binary classification problems. So suppose here we have 3 ordinal levels, one from 0 to 2. Firstly, we construct the first classification problem where the levels are determined by whether the ordinal level is larger than 0. And in the second classification problem, the levels are determined by whether the ordinal levels is larger than 1. So this just, if you have k ordinal levels, we will have k minus 1 binary classification problems. So we train our network by combining all these binary losses and do backpropagation. So here's a convergence curves of different losses. The x-axis is the number of iterations, and the y-axis is root mean square on the training data. So it's basically training loss. So the red one is obtained by the ordinal regression loss, and the green one is the multi-class classification. And the last one is the original trained using RMC. So we can see that even if we're training the network using root mean square, we cannot get the lowest root mean square on the training data. It's very interesting. So by replacing the regression loss by the classification or ordinal regression loss, we can actually obtain a better root mean square value on the training data. So we can get some much better local solutions in this case. And we can also see that ordinal regression performs better than the multiple class classification. So for the network, we design a multi-resolution architecture. Firstly, we apply a pre-trained network, usually pre-trained on ImageNet. For example, the VGG or ResNet, and then we obtain the high-level feature map F. On top of F, we extract multiple scale features by dilated convolution. So the first part is also we propose a 4-image encoder. So this 4-image encoder encodes the global information of the whole image, and these 4 branches extract multi-scale features. For the 4-image encoder, so previous works usually apply a fully connected networks to directly transform the feature map from VGG or ResNet to a final feature map. We found this is very inefficient, and also it uses a lot of parameters. So we propose a more efficient way to do this. So first do a pooling over the input feature map by strat k, and then we do a smaller fully connected network to transform this to a fixed length vector. And to enforce the global information, we do some further processing, and then we copy this single vector to all the locations in the image. So by doing so, we can all the locations in the image or in the feature map will share the same global information. For the multi-scale feature extractor, we employ the dilated convolution, which inserts zeros to a 3x3 vector to increase the filter size. In this way, we can have multiple scale filters, but this will not increase the number of parameters. And this one is a very widely used technique in semantic segmentation. So this is basically our method. So now I'm going to present some results. We evaluate the method using 4 metrics. So the first one is the scale event log loss. So it's basically the MSE loss in the log space, and by some correction for the bias in the estimation. The second and third one are relative square error and relative absolute error. The last one is the inverse RMSE. So we first do an inverse over the depth values and then calculate the root mean square error. So this is our results on a KT dataset. The first one is also our method, which is not used in the computation because it's trained only on a KT dataset. So the third one is our method. In this method, we train our model on KT and ScanNet together. Here we show some qualitative results. We compare our method with two previous methods. You can see that the estimate depth map from our method has much better quality than the outputs of the previous methods. This is the results on the ScanNet. Although we performed the best on this dataset, but you can see that all these methods are really close to each other, so it's not very significant. So to conclude, we found that casting depth prediction as an ordinal regression problem gains more robustness and speeds up convergence and obtains better local solutions. And also, aggregating multi-square information in parallel can be more effective than stage-wise refinement of the prediction maps. So here's the example on the real video. And the darker values means smaller depth values. It basically performs well, except that you can see here this human has a smaller depth, but it's basically wrong because here we only consider the visual 2D image information, so it's still a year post problem. It's very difficult in practice. And finally, if you want to know more details, welcome to our poster tomorrow from 12:30 to 2:50. Our ID is 3454. Thank you.
Thanks. I think we have time for a few questions. Also ask a question. So these two data sets here with Kitty and ScanNet are pretty different in terms of indoors and outdoors and depth characteristics. What do you think about generalizing to even different, more depth sensors or different, like landscapes and building facades, and as well as stereo indoors or something like this? Would you have to do anything different as well?
So this depends on how much data you have. Oh. Yeah. So if you have software data, level data in other domains, then basically you can just merge them and trade them together. But if you have, like in a new domain, you don't have level data, and you have to need to do like transfer learning or domain adaptation problem to adapt the model to the new domains. Yeah.
I guess you used all of them together. Yeah, no.
Oh, I know this one, right?
No, the loss functions used.
Loss function used. This one, or the evaluation matrix.
Evaluation.
Oh.
Oh, it's evaluation.
Yeah.
You didn't use those as the loss.
No. So the first one was used as a loss function for the regression problem, but the other three haven't been used as a loss functions.
So in your ordinal regression, you have a binary classification.
Yes.
Do you think you could learn more by extending that so that you have more information about the order, or is all the information encoded there?
Yes, because the method we used is very simple and very old one, proposed in around 2000. I think there must be more sophisticated ordinal regression methods up to now. Yeah, I think you can have a try. Yeah.
So which part is most important for getting good performance in your framework? Is it the loss function or the delta convolution, or?
I can say both contribute, but the loss function contributes more. And also this one, the discretization, the second discretization method is much better than the first one.
So do you have like a baseline experiments just analyzing one variant, like not mixing up all the stuff?
Yeah. I have one slide here, extra slides, and I will show it. Yeah, this some Appalachian Studies. So the first one is the mean square error, and we also try the mean square error on the discretization or discrete depths. So the performance is basically the same. This means the quantization error is very small in this case. And also we compare the loss function between the ordinal regression and multi-class classification. So basically, ordinal regression is better than classification and better than regression. And also the space increasing discretization is better than uniform discretization.
Why SID performs better in UD? Is it because most of pixels belongs to the foreground space?
Because most pixels are in the have small values, and in the larger values, the estimation error is usually very large. Yeah.
Let's thank the speaker again.
Thank you.
All right. And now we have Ke Xian.